And most of the time, our inputs are going to be x values. So numbers for x. And outputs are going to be y values. So a function, what it is it pairs an x value with a specific y value. And kind of in the bullet point below is a more formal definition of what it is. So when a relation is given as an ordered pair, so the x and the x coordinates are the input and the y coordinates are the output. So you ever see anything like this where it's just, we're talking about functions and you see a point, x comma y, know that we input something into our function did a rule, and then we got an output. The best kind of definition, or like real life, not definition, but real life example of what a function is a vending machine. I think when you go to the vending machine, there's a whole bunch of buttons, boom, 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 whole bunch of options. But usually in a vending machine, or the vending machine we're going to imagine, is each snack has its own button, and only that button. So if you want a Snickers, you have to press button 1. If you want M&Ms, you got to press button 2. Button 3 will always get you out of Butterfingers. So think, hitting the button 1 is our input. Getting out a Snickers bar is our output. Hitting the button 2, our input. 2, our output, a bag of M&Ms. Our input 3, we get an output of Butterfingers. All right. So each button has a specific pair, a candy that comes out with it. You don't want to go to a vending machine and say, all right, I'm going to press button number 1, and I could get out a Snickers, M&Ms, or Butterfingers. That's a broken function because that input doesn't have exactly one output. So the phrase that we're going to say, and what we're going to be looking for to determine if something is a function, is in this last bullet point. A relation is a function if each input has exactly one output. So maybe you can box that, star it twice. Because this is going to be a phrase you can use to just say something's a function. And I'll show you a phrase you can say if something's not a function. So you don't have to make it up yourself. All right. Think about it like in English, you'd use like a sentence starter. I'm basically just going to give you the sentence now, what you can say. So for these first few examples, we're given a set of points, and it's just asking us to determine whether each relation is a function, and it wants us to do a short explanation. So we're giving a bunch of ordered pairs here, and we're going to remember our x values are our inputs, our y values are our outputs. So as we're starting out, I'm just going to highlight all of our x values in yellow. I'm just going to write underneath it x, 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 x. In a second color, I'll highlight all my y values and label them y, 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 y. So think of this set of ordered points as like a number vending machine. When we input -2, we would get out a -2. That's one pair. Another pair. We input -1, we get out +2. Another pair. We input 0, we get out a 6. We hit 1, we get out a 10. We hit 2, we get out a 14. Right? Notice how each is unique. There's nothing that repeats. -2 only goes to -2. -1 only goes to 2. And so on. So what we would say is this a function? We would answer yes. And how do you know? We're going to use that little thing we box and we start. We're just going to use the definition. We're going to say each input, again, which is an x value, has exactly one output. Each x value only goes to one y value. If we plug in a 1, we're knowing we're getting out a 10. If we plug in a 0, we know we're going to get out a 6. Well, maybe more useful at this point is to see a counterexample of something that's not a function. So I'll tell you this one right away. Or is it a function? Oh, not yet. Not quite yet. X values, again, we'll go through. -3, -1, 1, 0, and 9. Those are all of our x values. Going through our y values. Remember, inputs, outputs. There's a lot of, what makes this tough, this section, is there's a lot of words we can use interchangeably. So I'm going to try to use as many of them as I can and keep using them. So again, think of a vending machine. If we hit -3, we're going to get out 9. There's no other -3 as an input. -1, we're only going to get out a 6. None of these other pairs show that I get anything else out when I plug in a -1. So I know, yes, this is a function because each input has exactly one output. Again, if you're someone that, again, colors help them, each input, everything in yellow, all of our x values, has one output. Our vending machine is working. We know what we're going to get out each time. All right. Information can be presented to us in different ways. Now our inputs and outputs are in a table, but this is the same as having a bunch of ordered points. This will be the point -2, 9, -1, 6, 0, 5, 1, 6, 2, 9, 3, 14. So all of our input values are up here on the top now. All of our output values, our y values, are all on that bottom row. -2, when we input -2, we get out a +9. When we input a 0, we get out a 5. When we input a 2, we get out a 9. So for each input, we have exactly one output. Our vending machine, we call it sometimes 1-to-1. One thing goes in, one thing goes out. So again, we could say yes, It is a function. And we keep using that same phrase. When something is yes, we know it's a function. All we need to say is each input has exactly one output. So you're going to ask to be able to identify functions in three ways. When they're given as points, when they're given in a table, and these last two examples are what we call maps. What it does, if you think of set A as all of our, we could also call set A just our inputs, and set B are the same thing as saying just all of our outputs. It kind of shows when you put something in with arrows what's going to come out. So looking at our inputs, so that oval on the left, -4, when we hit -4 on our number vending machine, it's going to give us a -3. -4 goes to -3. If we hit 5 on our number vending machine, it's going to pair us with a +7. If we hit a 2 on our vending machine, we could get a -3 or a -2, which is bad, all right? Because then it's no longer a function. Think if you go up to a normal vending machine, you want to get out a Snickers, but you hit a button, half the time you get out of a Snickers, half the time you get out M&Ms, that's not a very good vending machine, is it? So this is not a function because a input has two outputs. 2 can go to -3 or -2. It breaks the definition. The definition of a function is each input has exactly one output. And this function, 2, has exactly 2 outputs. So how we're going to write this, we're going to say, no, it's not a function. And how we're always going to list these, and we're going to say we're going to find the number that's messing it up. So it's 2. We're going to say 2 has an output of -3 and -2. That's basically like you telling me, well, Mr. Scully, this breaks the definition of a function because 2, number 2, is mapped to 2 different values. Our vending machine is broken. Again, when I'm doing these, the arrows are easy to get crisscrossed, so I like to just trace over them and check. 8 goes to -2. 8 only goes to one thing. My input only has one output. I go to 1. 1 only goes to 4. One input with one output. 9 only goes to one thing. 9 goes to +3. We have one input with an output. If I hit 9 on my vending machine, I know I'm getting out a 3. If I hit 2 on my vending machine, I know the only thing that I can get out is a -4. So each input has exactly one output. So we say yes. And then we use our handy dandy phrase. Each input has exactly one output.